Hello, everybody. We're going to start quite a long lecture on limits, but I'm going to split it into four parts. So we're gonna sort of talk about just very brief sections of limits in obviously one of four parts. Today we're going to talk about limits in terms of graphs. We're going to look at some examples, and we're going to look at this idea of left and right-sided limits and how those left and right-sided limits can sort of be joined together to make a limit in its entirety. So let's go ahead and start off with not any math, really. I just want to actually start off with an example. Let's say that I was trying to approach a wall. I'm going to make this wall right over here on the right side of my screen. So let's say I've got this pink wall here, and I want to approach it. So this whole idea of a limit is what happens as I move towards this wall. Let's say we're standing over here. We're nice and happy. Let's draw a person here. We're a person. We're standing nice and happy here. Let's say that I walk halfway towards this wall. So I end up right in the middle of the screen, right here. So if I walk halfway towards that wall, then great. I've moved closer to it. I'm closer to the pink than I was previously. Let's say I decide to move halfway again. And obviously what you could probably tell here is that I'm going to keep doing this sort of halfway idea. I'm going to keep moving halfway each iteration. Let's say I move half again on that third iteration. I end up right here. So hopefully you can tell that I am never actually going to touch the wall. If I keep moving halfway, I'm going to keep getting closer and closer to that wall, but I'm never going to actually touch it. And this is the whole concept of limits, is that as I do this sort of step halfway each time, 1, 2, 3, 4 times, I'm getting closer and closer to the wall, but I'm never actually touching it. That's, like I just said, that's exactly what a limit is. And so definitionally, what we can do is we can talk about a limit of a function f of x. We talked about functions last time in review. So we can say a limit, and I'm going to call that limit L. Okay, I'm just giving it a name, just calling it L. So a limit of a function at a particular point, right? So the limit of a function at a particular point, it's just the value that that function approaches at that point. So graphically, let's go ahead and do this. Let's go ahead and draw a graph. Let's say I've got something that looks like this, right? So let me do that in a different color. Great, we got a graph right there. There's f of x. I'm going to pick an x value here. And I'm going to say, all right, here's my x value. And I'm going to look at this function and I'm going to say, okay, as I approach that x value, what does my y approach? What does the function appear to be? And this is probably pretty easy to tell. As I come over here to my x, I'm going to go up to my y and I'm going to get right about here. So as I approach along this x value, basically as I approach along this function, I get closer and closer to that x. I'm going to get right here and I'm going to stop right there. And that right there is exactly the limit. It's the value of the function that I'm approaching. And so for a lot of these cases, it's pretty much just the value of the function at that point. If I change this, let's go ahead and change this from an x to a c. We'll use that letter c. Then the value of my limit L that I'm talking about, again, L just being the name that I'm using for that limit, that value is going to be whatever f of c is. And there we go. So that's the idea of this limit most of the time. We'll talk about some exceptions in a second, but just to start things off, it's basically saying, hey, if I start, if I'm up here and I'm a guy and I'm standing right here, and I sort of walk closer and closer and closer and closer to this x coordinate, where do I go? And that answer to that question, where do I go? That's the value of this limit. And so let's go ahead and look at an example here. If I have a function, y equals x squared, I've got it graphed out right here, if I look at x equals 2, you can hopefully see that if I plug in 2 into this function, I'm going to get out 4 because I'm going to take 2 squared. I'm going to get 4. So we'll see that here. 2 squared equals 4. That's good. So I'm going to get 4. And so if I'm looking at this x coordinate of 2, my y coordinate is going to be 4. But really what I want to emphasize here is that a limit is not just the value of the function. Yes, in this case, f of 2 is equal to 4. We can very clearly see that with this point. But what I'm really looking at is, as I approach x equals 2, what do my y values approach? And they clearly approach 4. That's because the function is equal to 4 at that point. But I really want to think about that idea of approaching 4, right? And so as you can see from either side here, if I approach x from either below 2 or above 2, my y value ends up approaching 4 in either case. And so we could say here that the limit of this function, and let me sort of highlight the definition as I say this, the limit of the function x squared at a point x equals 2, it's just the value that that function x squared approaches as x approaches 2. And that value is 4, right? That's that y value that that function approaches. So what we can say to make the notation a little bit easier, we can say that the limit of f of x as x approaches c is equal to L. And so just again, calling this out, just so we're not confused or anything. This c is an x value. Back on this slide, that c was equal to 2 right there. So this c was equal to 2. The f of x was that function, which on that last slide was x squared. And L is just the answer. It's just saying, hey, I approach that y value of 4, right? I get closer and closer to that as x gets closer and closer to 2. And so that L is going to be equal to 4. And this is just notationally what we've got here. I can sort of copy that down. Limit as x approaches 2 of x squared is equal to 4. We'll do several examples. We'll get used to this notation, but just want to introduce that right now. So we've actually just talked about right now how to graphically look at a function and figure out what the limit actually is. There are 2 other ways that we can do this. We can do it numerically and we can do it algebraically. For the majority of this course, we're going to work on this algebraically. Sometimes a graph can help you immensely. I'm going to give you guys an activity that you can work on your own that's going to teach you how to do these limits numerically. Numerically is the least rigorous of the 3, which is why I tend not to focus on it a whole lot during a lecture. Graphically is a great way to look at these, but again, not as rigorous as algebraically, but it's still a great way to sort of convince yourself of what a limit can be. Algebraically, I think, is the best way. It proves things, it gets it going right there. We know exactly what the answer is, and you know, we're off on our way. So again, just to recap, I know this concept of limits is very new. It's very different from anything that you've ever seen before. So just to reiterate, you've got a limit. I'm going to call it L, and that limit is just the value that a function approaches. And obviously there's an x coordinate that I'm talking about in consideration, but the limit itself is just the value that that function approaches. It's the y value that I approach as I approach another x value. Again, going back to this example with the wall, as I approach the wall, as I move closer and closer to the wall, you might ask yourself, okay, where do I start? Where do I eventually end up? Well, you end up at the wall right here because I'm approaching it halfway each time. And that's exactly that idea of a limit. Let's go ahead and look at some very straightforward examples of limits. This is a little bit algebraic, and as I've mentioned, we'll get into algebraic limits more in depth in the next parts of this lecture, but I just want to show some simple examples here. So if I have the limit as x approaches 4 of 3x, we've seen how to do this graphically. I could take this function and I could graph it, and I could say, okay, here is my graph for 3x. Boom, there's my line, y equals 3x. And as I approach x equals 4, right? I could just write 4 here, right? As I approach that 4 there on the x-axis, the question is, what y value do I approach here? And really what I'm getting at is, what is the orange point right there? What do I have right here on that orange? And what you're probably doing in your head, what you're hopefully doing in your head right now is you're saying, oh, I've got y equals 3x. And he's asking me, Ryan's asking me, why don't I plug in why don't I plug in x equals 4 into y equals 3x? Because that's going to give me this coordinate point right here. We have a coordinate point that's listed right there, x comma y. So if I just plug in x equals 4, I'm going to get out that y value. And what you should see is that you get out y equals 12, right? And so that's just a great way to do this limit. We've done it algebraically, but in essence, we've also done it graphically, right? We're doing it by just plugging in 4 into the function, but we've done it graphically by actually physically graphing this function, y equals 3x, and thinking to ourselves, what y value do I approach as I approach x equals 4? And again, keep that word approach in the back of your mind. It's always about approaching. That's all I care about. We're going to see this on the next slide, why that's so important. Let's keep doing these other examples. Let's say I had limit of e to the x as x approaches 0. I personally don't feel like graphing this. Maybe I forget what e to the x looks like. Hopefully I don't. But maybe I forget what e to the x looks like, and I don't feel like graphing this. So what I can do is I can just take this and I can plug in 0 in for x. And if I do e to the 0, I get out 1, right? We could do the same exact thing on this 2x squared here. I could plug in -3 in for x. And if I do that, that -3 squared is going to become 9. Then I'm going to multiply it by 2, and I'll get 18. And so these are going to be the values of those limits. Now, here's a tricky one. Limit as x approaches 7 of 2. Now, you're probably looking at this, you're like, where's the x? There's no x here. How do I plug in for 7? How do I plug a 7 in for x if there's no x? Well, this is a great example of where I can actually graph this thing. So if we graph this graphing of 2, that's just going to be a line at x equals 2. Let's get this in a different color. So that's just that graph at x equals 2. And so if y equals 2, I said x equals 2, I meant y equals 2. So now, if I look at that value of x equals 7, and I ask myself, all right, as I approach x equals 7, oh, that's a bad color. Let's go ahead, let's go green here. As I approach x equals 7, what do my y values approach? And you can very clearly see that those y values approach 2. It's just 2 all the time. And so in that case, that the value of this limit is equal to 2. I'll go ahead and write that here. This value is 2. On this top one, remember, it was 12. I didn't write that explicitly, but there we go. That's 12. So the value of that limit is just 2. We've done that algebraically. We've done it graphically. You could do it algebraically by just saying, let's plug in an x equals 7. Oh, there's no x? All right, I just get 2. Okay. We're going to see plenty more examples of this algebraically next time. So if doing it algebraically is a little bit weird, don't worry. Just think about it graphically, and we'll get there on the algebraic sense of this limit. So let's go ahead and look at another example here. Here's the work for that last stuff that I did. Let's take a look at this graph here and look very carefully. I have a hole right here. So the function itself, this y equals g of x, granted, it does look an awful lot like an x squared graph, but it's not quite exactly x squared. And that's because I don't have any value at this point right here. There's a hole there. And remember, we see holes when we have fractions, when we have things canceling. We'll get into that in a second. But we have a hole here, and so there's no function value at that point. So the question I'd ask to you is, well, what's the limit, right? Again, that word approach is key here. As my x value approaches 2, what does my y value get closer and closer to? And as I approach 2, my y values approach 4. Now, let me be very clear. When x is equal to 2, I don't actually have y equals 4. When x is equal to 2, there is no y value for this function. We have a hole right there. But as I get closer and closer to 2 for x, my y approaches 4. And so in this case, it's actually the same answer. We still get 4 for our answer for the limit, just like we did back on this slide here. When we looked back here, we said, hey, I've got a function, x approaches 2, and oh, look, y approaches 4. Well, even if I take this point right here, 2, 4, and I make it a hole like I have here, if I make it a hole, the function still approaches 4. It gets closer and closer to 4. I mean, follow it along this line. You can see as I get closer and closer, my y is approaching 4. Even if I come from this side, my y is approaching 4. I never actually get to 4, but I get very, very, very close to it. And that's this whole idea of a limit. Again, if I walk closer and closer to that wall each time, do I ever touch the wall? No. Do I get close to it? Am I approaching the wall? Yes. And that's the whole question that we're asking ourselves is, what the heck am I approaching here? So let me throw out another example for us. It's going to look very similar to this slide, but I'm going to switch over here. So the big difference here is this point 2, 1. And so here's the question I'd ask to you is, what is the limit of this function as x approaches 2? And what a lot of people tend to say is they tend to say, oh, well, let's look at this y value here. When x is equal to 2, I've got the point 2, 1. So the limit is y equals 1. That's the limit, is 1. But that's actually incorrect. I agree that the function is defined at this point 2, 1. But again, like I keep saying, I don't really care about the limit, or excuse me, the function being defined at a particular point. I care about the limit and where it's approaching, where the function is getting closer to. And as I get closer to 2, I keep saying this, but that's okay. I'm gonna keep repeating myself. As I get closer and closer to x equals 2, my y value, it gets closer and closer to 4 up until I get exactly on 2, and then I jump down here, and then I come right back up, and then I keep going. So as I approach this point, I get closer and closer to 4. At that point, I'm getting closer and closer to 1. But as I approach it, I'm getting closer and closer to 4. And with limits, that's really what we care about. I could care less what the value of the function actually is at that point. I just care about what it approaches. So that's kind of it as far as graphs go for a little bit. Let's go ahead and look at an algebraic limit here. So we're going to go ahead and look at this limit as x approaches 2, and we're going to have a rational expression here. So we're going to have an x cubed minus 2x squared divided by x minus 2. And what I can hope you guys see here is if we're going to do this algebraically, we got to be a little clever. And the reason I mentioned to do this algebraically is because doing this graphically would be tough. When I look at this function right here, oh, excuse me, sorry, my iPad kind of freaked out there. Let's pop back. There we go. There we go. So if I'm going to, like I was saying, if I'm going to look at this function right here graphically, I'm probably going to have to use a computer to graph that. I don't know what that looks like off the top of my head. But that's okay, because graphically that's tough. I mean, we don't want to use a computer if we don't have to, right? So we can do this algebraically, and hopefully what you can see is that this numerator, I can factor out an x squared. And I'm going to go ahead and do that right here, and go ahead and follow along with my work as I factor out that x squared. All right, so I'm going to factor out this x squared on the top. And you'll notice I'm left with an x minus 2. And voila, things cancel very nicely. I have an x minus 2 on the top. I have an x minus 2 on the bottom. They cancel. And so what I'm left with is the limit as x approaches 2 of just x squared. And guess what? We've seen this, right? This is exactly what we just had graphed on that last example. We had the function x squared right here. We were taking the limit of it as x approaches 2. And in fact, this graph, or this function right here, is this graph right here. That right there, if you actually went on to like Desmos or Wolfram Alpha and you looked and you typed this in, you would see exactly something like that. And so again, what we're looking at here, when I do this limit as x approaches 2 of x squared, we're going to do this algebraically. I'm going to plug in 2 in for x. And so when I do that, I'm going to get 2 squared, which is equal to 4. And that's my final answer right there, is getting 4, right? Now, I kind of jumped into this and I just said, hey, let's factor. Let's just jump right into this algebra and let's factor so that we can cancel our x minus 2s. That's me just kind of knowing that that's what's going to happen. But obviously, if I'm giving you an exam or something like that, you don't know right off the bat that that's going to happen. So what you would probably do is you would try just plugging in 2 into this function right here and see what you get out. And I recommend for you to do that for a quick second, maybe even pause the video. Try plugging in 2 into this function right here and see what you get out. Now, I bet if you did that, if you actually just plugged in 2 into this function, you probably got 0 over 0 if you plugged in 2 into here. Let me actually go ahead and do that. Plug in 2 cubed minus 2 times 2 squared all over 2 minus 2. I get 8 minus 8 all over 0. I get 0 over 0. And when we get 0 over 0, we are both happy and sad. We're sad because 0 over 0 is not something that we like to get. It is not a viable answer. I will not give you any credit if you put 0 over 0 and box your answer. But we're happy because it tells us very explicitly that we're not done with the problem. It lets us know that we have more work to do. We call this 0 over 0 an indeterminate form. And there's a reason we call it an indeterminate form. That word indeterminate is key here. So think about these 2 rules that we have. And these are just sort of general math rules. If I take any number, let's say I take the number 7. I'm gonna give myself a new page here. Let's say I take the number 7. If I do 0 divided by that number, I get 0. And so you sort of think about this rule that 0 divided by something equals 0. If I take 0, I divide it by anything. It doesn't matter, I get 0, right? But then there's this other rule that if I take 5 or some other number and I divide it by 0, that doesn't work. We've always heard this phrase, you can't divide by 0, right? And so the reason we call 0 over 0 an indeterminate form, it's because it's unable to be determined. If I get this 0 over 0, I can't actually say what my answer is because we have two conflicting rules. I have 0 divided by another number, which should be 0. But I also have a 0 on the denominator, and that's bad. We can't have that. So in this case, we just can't determine what the heck our answer is. So we call it an indeterminate form. And if you get this indeterminate form, if you ever get 0 over 0, I'm going to harp on this over and over and over. If you ever get 0 over 0, you are not done. That is not a viable answer for this limit. You have to do something else to this problem in order to finish it out and actually tell me what the limit is. And we did that work already. We did that here. We did the factoring, we canceled, we plugged in. That's all fine and fantastic. But in the very first start of the problem, you would probably recognize that you'd get 0 over 0, and you'd say, that's bad. I can't do that. I have to do something else. And that something else you do is exactly this factoring that you already saw me do before. I factored, I got a little bit lucky, and I canceled stuff. When I canceled those things, I just ended up with an x squared. I can then plug in 2 into the x squared. I get 2 squared, which is equal to 4. And we're on our way, and we're actually done with the problem at that point. And so that's this whole idea of evaluating a limit algebraically. The phrase that I haven't used in here, we've been doing it, but I haven't actually said this explicitly. It's called direct substitution, or just substitution, some people will call it. And we did it, really. We did substitution right here when I just took the limit and I took the x equals 2 and I just plugged it in everywhere I saw an x. I just went, let's just make it equal to 2. And I just plugged it in everywhere, and we went on our merry way and we did our algebra. That's called substitution. I'm directly subbing in that x equals 2 into the function everywhere that I see an x. And so in this work right here, where I ended up with a 0 over 0, I immediately started off with direct substitution. And in general, that's always what I want you guys to do. Always start with direct substitution. If you get 0 over 0, like we did here, that's fine. It just means that you have a little bit more work to do. And again, that work is just this factoring that we did. And so once you do some other work, in this case, factoring, we're going to look at some other examples tomorrow of that type of extra work that you can do. If you get 0 over 0 initially with your direct substitution, you do some fancy algebra, maybe factoring or something else. You cancel some things or you do some other algebra. We'll get into all that next time. But you do something mathematically, and it gets you to this point where you just have a very simple limit. And at this point right here, what I've got boxed, if I do direct substitution on that, I'm going to get my answer of 4 right there. I'm just going to directly take that 2 and I'm going to plug it right in for that x. Just boom, straight in there, plug in 2 for x. I get 2 squared. Just fit that in there. I get 2 squared, and that's equal to 4. Just nice and simple. And we're done. We get 4 for our answer. So that's that whole idea of an algebraic limit. Great. So what I want to talk about next are going to be left and right-sided limits. So let me pop back to a graph that we've seen before. Yeah, sorry, I went a little bit too far. Here we go. Here's a graph that we saw before. You can see that these limits here, I'm looking at this from both sides. And I've drawn these arrows before. I've drawn it from the left and I've drawn it from the right. What we can do is we can ask ourselves about a left and a right-sided limit. So we can say, what if I just approached from one side as opposed to both? And if we do that, we have a little bit of different notation here. So what we'll do is we'll say limit as x approaches, that arrow meaning approaches, c, just whatever value, whatever x value I'm approaching, but I'm going to approach it from the left, denoted by a negative superscript, or from the right, denoted by a positive superscript. And when I do that, I'm talking about a left-sided limit or a right-sided limit. Some people will just say left limit or right limit. I'm fine with either. I generally tend to say left-sided or right-sided, but it's up to you. I'm fine with whatever. And so we're talking about a limit just approaching from one side. So again, if I go back to the graph, let's go ahead and come back here. Yeah, if I come back to this graph here, if I'm talking about a left-sided limit, I'm going to look just as I approach from the left. I could care less about anything over here. I don't care about anything on this right side. That's just all a bunch of garbage to me right now. I just care about what happens as I approach from the left side. If I look at a right-sided limit, I could care less about anything over here. I just don't care at all. I'm going to cross all that out. I just care about what happens as I approach x equals 2 from the right side. And that's just that right-sided limit. We've got that notation there that we'll use where we have that superscript of the minus or the plus. Great. So we've got left and right-sided limits. We've seen this. If we take a left-sided limit, we look at just the left side. If we take a right-sided limit, we look at just the right side. So, and actually, I was going to get into some other limits, but let me say one more thing about left and right limits. We'll talk more about this later, but in order for a limit, just a general old limit, in order for that to work, you need the left-sided and right-sided limits to be the same exact value. We're going to look at this more in depth later, but just to give you guys a little bit of a preview at it. In order for a limit to work, it has to work from both sides, which means that those left-sided limits and the right-sided limits, they have to be the same thing. So we'll get, like I said, we'll get into that more later, but I just wanted to mention that while we're here talking about left and right limits. Let's go ahead and wrap up talking about some bad limits and weird things that can happen with limits. And because sometimes if I give you a limit, right, it actually might not even exist. We saw back here on the graph, we saw here, this was perfectly fine. The function did not exist at this point, or excuse me, let's look at this graph. The function did not exist at x equals 2. But the limit exists because the function approaches 4 as I get closer and closer to that point. The value of the function is nowhere to be found. There's no hole filled in right here. In fact, there is a hole right there. There's just nothing there. But the limit is 4. And so there are three main ways. There's obviously a lot of ways, but there are three main ways that a limit can actually just not even work. And one way is if the function approaches infinity as you get closer and closer to your point. We'll look at an example of this in a second. Let me just go ahead and go through two other ways. The second way is actually what I just said before. If the left and right-sided limits are different, then your function, your limit itself does not work. And again, we'll see a graphical example of this. So I'll get into that. The third way is craziness. I won't even bother to explain that yet. We'll just see a graphical example and you'll know what I'm talking about. So let's go ahead and let's get into a graph example of this first idea. F of x approaching is infinity. So here I have a graph of e to the x, or just 2 to the x, or some sort of exponential. And the question that I would ask you is, as x approaches infinity, as x gets really, really, really big, so x is here, that's great, that's all fine and dandy, you know, I've got an x value right here, but as it gets bigger and bigger and bigger and bigger, and it gets way out here, right, what does my y value on the function approach? And to me, it looks like that y value, it kind of just goes off to infinity. I mean, it just keeps going forever and ever. I mean, you can't even see where it's going. It's just disappearing from the screen. It just goes on forever, right? And it goes up to infinity. And so I would say that this limit here, it actually is equal to infinity. And that's a problem. That's sort of a problem for now. We'll talk about infinite limits a little bit later. But for now, this is a problem. I don't like that because I don't have a specific answer for my limit. I don't have a number like 17 or 4. I can't say exactly what that limit is. It's infinity, which isn't even a number. It's just this concept of being really, really large. But that's exactly why I don't like it. It's not a number. It's not a specified number. It's not just a very sort of concrete idea. Here's another concept. If I take the limit as x approaches negative infinity, so as x goes this way, as I get smaller and smaller and smaller and smaller, and I go way over here, my graph, this red line, this red curve, it approaches 0. And that should be very, very clear to see, is that as my x gets smaller and smaller, as it gets more and more negative, my y value approaches 0. And that's fine. That's good. I like that because that gives us a definitive answer of 0, right? This is also a great example of how the function itself, this f of x right here, it's never equal to 0, but the limit of f of x approaches 0. And that's kind of this idea of limits. Again, it's all about approaching. It's not about the actual value. But this top example here where I get infinity, that's one of these ideas of where the limit fails to exist. Sometimes what we'll say instead is we'll say that the limit does not exist. In this case, I'm not a fan of that. So maybe I just say, don't even worry about that for now. I'll get into that actually on the next, on a couple slides from now, not the next slide, but a couple slides from now, I'll get into that does not exist nonsense, if you will. Great. Let's go ahead and continue on with some more bad limits. So here we're looking at the function 1 over x. Hopefully you can tell that just by looking at it. And we're going to look at a handful of limits. We're going to look at 3 of them. And these are some left and right-sided limits. So let's go ahead and look at the limit from the left side first. If I take a limit as x approaches 0 from the left, and again, that's me saying 0 from the left. That's that negative superscript on that 0 right there. As I look at the limit as x approaches 0 from the left, I've got 0 right here. That's x equals 0. That's all fine and dandy. I'm going to look at this from the left-hand side. And as I approach this, if I'm standing over here, if I'm just having a good old time and I'm standing right here, as I walk closer and closer to 0, my y value approaches negative infinity. It just goes down and down and down and down and down. It just keeps going on basically forever as I approach 0 from the left. And so what I would say here is that the answer to this limit, the limit of this function 1 over x, as x approaches 0 from the left, it approaches, the y value approaches negative infinity. And so that's exactly sort of where I'm heading towards. If I'm a person and I'm walking along this graph, I'm approaching a y value of negative infinity, that y-axis right there. I'm approaching negative infinity. However, if I flip this around and I approach from the right-hand side, if I'm here and I approach that 0 from this side, and I get closer and closer, I actually tend towards positive infinity, right? I go up and up and up. I follow this I follow this function here and I just keep going up and up and up forever. And I get closer and closer to infinity as I get closer and closer to 0. And so this is that whole idea of left and right-sided limits. You can look at each side of the function. You can look at each side of x equals 0, from the left of 0 and from the right of 0. And you can actually get 2 different answers. And if you get 2 different answers, like we do here, we get negative infinity and positive infinity, that is exactly when we say that the full limit, just as x approaches 0, it does not exist. And we'll abbreviate that with DNE. And what I mean by it not existing is it's kind of exactly that. It's that the limit doesn't exist. There's no value for it. As I approach 0 from the left and from the right, I don't get a definitive value. I get either negative infinity or positive infinity. And I can't say which one I get if I just approach from both sides at the same time. And so we sort of have this conflict. We've got a sort of a tug of war. Hey, is it negative infinity or is it positive infinity? Is it negative infinity or is it positive infinity? And we just can't answer that question. So we say that the limit does not exist. Awesome. Let's go ahead and look at another example. This graph right here is a logarithmic function. So we're going to have like f of x. I don't know exactly what the base is. That's fine. We'll just say log of x. The base might be log base 2. It could be log base e. It could be log base 34. I don't really know. We'll just say log of x. There we go. And now I'm going to do 4 limits here. I'm going to take a limit as x approaches infinity. And what you can see here is that as my x value gets bigger and bigger and bigger and bigger, and as I keep going out on this direction here, as I keep getting larger and larger on my x, my y value gets bigger and bigger and bigger. And so this value of this limit would actually just be infinity right here. And again, like we said before, that's bad. I don't like getting infinity. It's not a specific answer. It's not as nice as just getting 32 or 3 or -8. Those are very definitive answers. Infinity is a sort of a bad answer for now. We'll talk more about infinite limits in a couple lectures, but for now, we're not really a fan of that. It gives us infinity. It's not anything definitive. Let's go ahead. Let's actually jump down to this third guy right here. Let's look at the limit as x approaches 0 from the right. So I've got x equals 0 right here. That's just that axis. I've got x equals 0. That's good. I'm going to approach this from the right-hand side. And if I follow this function as I approach from the right-hand side, my y value approaches negative infinity. It just keeps going down and down and down and down as far as your heart's content. And that's exactly why we would say that this limit is negative infinity. It just keeps going on forever and ever and ever. Now, if I look at this limit from the left-hand side, or excuse me, 0 from the left-hand side, that's a problem because the function isn't even defined on the left-hand side. If I look over here in this whole region here, there's nothing over here. There's no function. The function just exists for positive x. That's the only spot that it actually even exists for. So if I try to approach 0 from the left-hand side, there's not even y values for me to look at over here. There's just nothing, there's nothing to even look at. So in that case, I can't even tell you what the limit is. That's again when we say does not exist. And then again, like we saw on the last slide, my left and right limits don't match up. So if I look at the limit as x approaches 0, there's just no way for me to say, oh, from the left-hand side and from the right-hand side, it approaches the same exact thing. And so I can't actually even tell you what the limit as x approaches 0 is. Now, let me be very clear. As I approach from the right-hand side, that's when I get that negative infinity. You can very clearly see the graph goes down to negative infinity as my x's approach 0 from the right-hand side. But when I don't specify that side, I have to look at it from both the right and the left side. And if I do that, because that left side is sort of a no-go zone, there's no function over there, I get dne on that left side, there's no way for me to answer this limit, so we just say dne. And then that's kind of just what we're left with. All right, another example here, this will be our second to last example, penultimate example here. Let's say we have a function that jumps from one point to another. This function would not be continuous. We'll talk about the idea of continuity in much more detail later. But this function is not continuous. I can't draw this function without lifting my pen up. If I start tracing over this function, in order to get up to the rest of it, I have to lift my pen up. You can see that it'll highlighting it, it'll disappear because I've lifted up my pen, right? I can't do something like that because the function, there's no line here. The function doesn't exist there. No one drew a line right there, right? And so let's do some limits here. If I take a left-sided limit as x approaches 1, so I'm going to have x equals 1 right there. I want to do a left-sided limit, so I'm going to ask myself, what y value does the function approach when x equals 1? And I'm going to look at this from the right-hand side, or excuse me, from the left-hand side. And if I look at this from the left-hand side, I'm looking on the left side of this. I don't even care about anything over here. I'm just going to scratch all this out because we don't care. We don't even need to look at it. I'm just going to look on the left-hand side, and I'm going to see, hey, look, if I draw a line, along the function, I just trace it out. As I approach x equals 1 from the left-hand side, my y value is approaching -1, right? This point here is 1, -1. So that's the value of my limit right there, is that -1 as I approach from the left-hand side. And so we'd say that this left-sided limit is -1. As I approach from the right-hand side of 1, I have to trace along the function here because this is to the right of x equals 1. And as I approach that, my y value actually approaches 1 right here. Now, let me be very clear. The function is not defined up here. It's defined down here. The value of this function when x is equal to 1 is given by this coordinate, which is -1. But I don't care about what the function is defined as. I care about what the function approaches. And that's why the answer here for this right-sided limit is going to be +1 as opposed to -1. Finally, we've seen this before. We have a discrepancy between our left and our right-sided limits. So as I try to approach 1 from both sides of it at the same time, I have this disconnect here. I have a positive and a -1. I have a plus or -1 that I'm trying to approach. And so we end up having does not exist for that limit. Awesome. The last example that I want to go through is this craziness that I talked about. And this actually is a real function. I've typed this in. It is the, my software that I use has output this graph. This is a real graph. And as you can see, it kind of oscillates. It kind of goes up and down. Let me draw a little better. It goes up, it goes down, it goes up, it goes down, and it just starts to get all sorts of crazy in there. And then it kind of peters out and it goes down and it goes up and it goes down and it just keeps doing that. And in this case, you just have craziness going on. There's no way to know sort of what's happening in here because the function is just going up and down so crazy. that there's just no way of knowing what's actually going on in there. And so in this case, we actually can say that as x approaches 0, as I get closer and closer to 0, so as I follow along this curve, up and down and up and down and up and down and up and down, as I approach x equals 0, I just have no idea what my y value goes to. So I'm going to say does not exist here. And again, that's that sort of last example of a bad limit, why we would say it does not exist. Awesome. I'm going to leave it at that for this first lecture on limits. I know that's been a lot. Try and digest that. We're going to see 3 more lectures on limits, and I'll go ahead and stop this recording now so that we can move on to the next ones.